In Chapter 4, we're going to talk about reactions in aqueous solution. This is basically a review of reactions that you probably have had before in another chemistry class, and it might be an introduction for the first time to some kinds of chemical reactions. Why in aqueous solution? Well, lots of reactions happen in aqueous solution, for one thing. It's very common because the ions are free to move around, and the particles can get together with each other, and so it's a conducive place for chemical reactions. But it also gives us a good opportunity to talk about water and its importance in chemical study and in the everyday life that's governed by chemistry. We're going to start out with this Quizkin, just a little review of an analysis. This one's a little more complicated than what you might have seen before. Take a look at it and stop the video, try and solve it. I'll give you some answers in a bit. Well, if I analyze this problem, here's what I know. I know that I have 4.649 grams of this Na2S2O3, sodium thiosulfate it's called. What's my objective? What I really want to know is what percent of this bronze is copper. So it would be X grams of copper. That's my unknown. That's really my objective here. Divided by the total mass of the sample, which is 2.053 grams. So that's where I got to go. I got to find that. It's essentially a stoichiometry problem. So I'll start out by writing down 4.649 grams Na2S2O3. That's my starting point. What's my ending point? Well, at some point here, I want to get to grams of copper. That's my objective in the end. Well, I can't do any stoichiometry without using moles. So I've got to convert this to moles. I'll use the molar mass of this substance. 158.109 grams per mole is what it works out to. And that gives me moles of Na2S2O3. What am I going to do with that? If I look at the last equation there, I see that there's a ratio of 2 moles of Na2S2O3 to every 1 mole of elemental iodine, I2. And then if I look at the next equation up, I see that 1 mole of I2 reacts with 2 moles of copper 2 sulfate. And then if I look at the first equation, I see that 1 mole of copper 2 sulfate reacts with 1 mole of copper, or is formed by 1 mole of copper. So looking at my factors here, I've canceled off moles of sodium thiosulfate and moles of iodine, they're gone, and moles of copper 2 sulfate, they're gone, and all I have is moles of copper. I want grams of copper, however, so I'll multiply by copper's molar mass, which is 63.546 grams per mole, and this will give me how many grams of copper. I should have 4 significant figures, and it works out to 1.868 grams. So then the last thing I have to do is plug that into my original starting equation here and find out the percentage. So it's 1.868 grams of copper divided by the total mass of 2.053 grams. And then I want to express this as a percent, so I multiply by 100. I should have 4 sig figs still, and it's 91.01% copper. Today's lesson is going to be about 2 things. One is water, and the other one is solutions. We're going to introduce water briefly by talking about some of its features and characteristics. First of all, water is one of the most important substances on Earth, and it's water's unique chemical makeup that makes it so important. It's extremely important in the study of chemistry because it dissolves lots of things, especially lots of things that are important to life and to other things that we're interested in studying. So water has a very important role in the study of chemistry in addition to ordinary life. Here's its chemical composition. Chemical composition of water is it's 11.19% hydrogen by mass, and the rest, 88.81%, is oxygen. Now, if you think about this simple familiar formula of H2O, this doesn't look right. It looks like there should be twice as much hydrogen as oxygen. But hopefully by now you're catching on to the idea that mass and moles don't have the same ratios. Hydrogen weighs a lot less than oxygen. Here's the molecular structure of water. You can see the way that this is sketched out here, which is true to what we believe about water's structure. It's got a bent shape, and in fact this is a tetrahedral geometry, if you recall that, from previous studies, which leaves the molecule as a bent molecule with a 105-degree angle. It's a bent 105 molecule. That turns out to be important. If it was linear, it wouldn't be polar, and some of the most important features of water have to do with the fact that it's polar. So let's talk about the intermolecular forces that are in water, which are mainly why water is so important. Between molecules of water, like here you see we've got 5 water molecules. Between water molecules, there are forces that hold the water molecules together. Those water molecules are held together by a pretty significant force that's called a hydrogen bond. Here's how it happens. 2 factors about water molecules make this occur. One is the water molecule has 2 OH bonds in it, and those bonds are pretty polar. The oxygen end of the bond is more electronegative. In other words, it has more of an attraction for the electrons in the bond than the hydrogen end is. And so the electrons that are in these 2 bonds spend a lot of their time on the O end of the bond. So that makes this end kinda negative. The symbol we use for kinda is the small letter delta from the Greek. And the other side of the water molecule is kinda positive. Not a full charge, but there is more negativeness on the O end than on the H end. If it weren't bent, those 2 little arrows, those dipoles that I've drawn, would cancel each other out, and this wouldn't be true at all. Now, in addition to that, each oxygen has got 2 lone pairs that are pretty attractive for positive things. So the positive H end of this neighboring water molecule is strongly attracted to the lone pair on that oxygen. And the same thing is going to be true over here and here. So every water molecule, like take this central water molecule as an example, is strongly attached to 4 other water molecules by this strong hydrogen bond. This makes a few very interesting physical characteristics of water that make it so important. Here's one. It has a high boiling point. Water boils at 100 degrees C. Nitrogen, on the other hand, has a very similar structure and in fact does hydrogen bonding. But because it can only do hydrogen bonding in one spot, having 1 lone pair, it boils at negative 33 degrees C. They're very similar in size, similar even in structure, but that additional hydrogen bond on that water molecule makes it boil at a much higher temperature. Another feature of water is its high specific heat, and this is also caused by the fact that it has such strong intermolecular forces. Specific heat is how much energy it takes to raise a certain amount of water by a certain temperature, and it's 4.184 joules of energy to raise 1 gram of water by 1 degree C. This is incredibly high. Here's what most metals and other solids are. They're less than 1, typically in the 0.1 to 0.5 area. So water is a whole order of magnitude better at resisting temperature change, and that makes it extremely important to us. We would not be able to live on this planet. It would be hundreds of degrees above zero and near absolute zero temperature ranges. Very, very incredibly hot sunny days and very, very, very cold nights. And water, because it's so hard to increase and decrease the temperature because of this high specific heat, regulates the temperature of our planet and keeps it livable. All because of water's molecular properties. It also has a very high heat of vaporization. The heat of vaporization of water is 40.79 kilojoules per mole, which means to vaporize water, a mole of water takes a lot of energy. Compared with other substances, this is pretty big. And that keeps the water from evaporating off of our planet and keeps it here in the liquid form with its high specific heat. Why does it have a high heat of vaporization? Well, vaporizing is just tearing a water molecule away and putting it out into space in the gaseous form. And it's hard to do that when the hydrogen bonds are there because they're so strong. Here's something for comparison. Remember, water is 40.79 kilojoules to vaporize a mole. H2S is a very similar structure. It looks almost identical. The difference is the polarity of this molecule is less than water. What's the result? Well, hydrogen sulfide only takes 18.66 kilojoules to vaporize a mole, and that's much more typical of most substances that are this size. Another feature of water is that it's less dense as a solid than as a liquid, and that has to do with the fact that these intermolecular forces cause water to organize itself in a space-filling way when it gets cold and can't move around anymore. So here's liquid water over here. The liquid water, you can see the particles are packed closely together because they can jumble around and fill up the spaces. But as soon as it gets cold enough that the particles aren't moving around fast anymore, they snap into these rigid locked positions and they make this sort of a ring structure. It's three-dimensional, but you can sort of see where there are these open holes. That makes the water take up less space when it's a solid. There are fewer particles in the same amount of space, and as a solid, it's less dense, which means it floats. And that means that lakes, ponds, rivers, streams all freeze from the top down rather than the bottom up, and that allows aquatic life to live through the winter. And that's important because aquatic life is at the bottom of practically every food chain, even the ones that we're part of. And so it's extremely important to us that water happens to be less dense as a solid than a liquid. And it's also very unique. There are very few substances that are less dense when they're a solid than when they're a liquid. And then in terms of chemistry, the reason these intermolecular forces are so important is because they come from polar molecules. And this makes it possible for water to easily dissolve polar molecular substances. It has a high solubility for these things, so other things that have those dipoles that can do hydrogen bonding, and ionic crystals, anything that's charged, like a salt. Well, let's talk about solutions, and in order to do that, there's a bunch of terminology that we got to get out of the way so you can understand what it all means as we continue to discuss solutions. One is solvent. Solvent is the medium into which the solutes are dissolved. This is usually the largest part of the solution. I'll use Kool-Aid as an example of a solution because it is. You dissolve into Kool-Aid a little sugar and a little bit of the stuff from the packet and a lot of water. Water is the solvent. That's what everything gets dissolved in. The solute is any substance that's dissolved in the solvent. So the sugar, the Kool-Aid, whatever is all in that Kool-Aid packet, those are solutes. Concentration is a way that we talk about the measure of the ratio of solute to solvent. In common terminology, we could say, how strong is the solution? If you make Kool-Aid according to the package directions, that's normal. If you make it with too much water, that's weak, or the word that we use is dilute. Here are a couple of ways we can describe concentration, kind of in a relative qualitative way. When the ratio of solute to solvent is relatively low, we call that dilute. So if I make Kool-Aid and I don't put enough of the Kool-Aid stuff in there, I have a dilute solution. Or on the other hand, if I had put too much water in there, it's dilute because the solvent is too big. Concentrated solution, the ratio of solute to solvent is relatively high. So if I make Kool-Aid with 1 quart of water instead of 2 quarts, I would have concentrated Kool-Aid. These are relative terms. Everybody kind of has a feel for what Kool-Aid is supposed to be like, and so we know if it's dilute or concentrated by how it would taste. But in other situations, like when you're talking about some solution in a laboratory, well, it's not so clear, and without some kind of a standard or reference point, it's not so helpful to use these descriptions. Another way we can think about solutions is how much can you dissolve? All of us have probably had the experience of trying to dissolve sugar in tea or some other beverage, and you can only add so much sugar, and pretty soon it stops dissolving. When it stops dissolving, you have what's called a saturated solution. That means no additional solute can be dissolved in the solution. Now, you could dissolve more in there if you made it hotter or if you changed the pressure, perhaps. But at a given temperature and pressure, you've reached the maximum amount of solute that you can dissolve. An unsaturated solution just isn't there yet. It contains less than the saturation quantity of solute. And then it is possible by a trick to make something called a supersaturated solution. A supersaturated solution contains more than the saturation quantity of solute at that given temperature and pressure. Let's take a look at this beaker here. and imagine that I have a solvent in here, and then I put my solute in the bottom. If I add solute and stir it up, the solute goes away. It dissolves. So in unsaturated solution, you can't see any solute in it. If I have a saturated solution, that means I've dissolved as much as I can, and there's still a few crystals of solid down here at the bottom. So this is undissolved solute that's laying in the bottom. It's reached a point where you can't dissolve any more solute. It's saturated. Essentially, the water has become too crowded to fit any more particles in there. Now, if I were to heat this up, make the temperature go higher, for almost all solutes, here's what would happen. The solute that was in the bottom would suddenly dissolve. It would disappear because this dissolvability is higher at a higher temperature. So it would dissolve. And then if I cooled it down very slowly and carefully, I would have a supersaturated solution. So if I see crystals in the bottom, it's saturated. If I don't see crystals in the bottom and I know it's a solution, it might be unsaturated, but it also could be supersaturated. Solubility is a word that we use to describe quantitatively how much solute is needed to make a saturated solution. This, of course, has to have a specified amount of solvent, and it also has to specify what is the temperature and pressure, because that's going to change the solubility. Hot tea, for example, dissolves more sugar than cold tea does. And you also have to have a reference point. And so this is often given in grams of solute per like 100 grams of water, or grams per liter, or something like that, or sometimes moles per liter. The process by which solute and solvent become a solution is called solvation. And in this chapter, we're primarily focusing on water, so I'm going to illustrate this by using water, but it's also true for other solute-solvent situations. In this example, we're going to use an ionic crystal and water. So the first thing that happens is water molecules attract one of the ions that are at the edge of the crystal. For example, these water molecules that are up here in this corner have their positive end, their H end, in, so they must be near a negatively charged ion. There's an attraction between those things because opposites attract. Then the random motion of the water molecules shakes the particle loose from the crystal. And we're going to see it get shaken loose here and dragged out into the solvent space. And then they get surrounded by water molecules, and now each particle from the original crystal is surrounded by enough water molecules to make a kind of a shield. And if you look closely, you can see that the O's are facing in on the positively charged ions, and the H's are facing in on the negatively charged ions. This keeps the particles surrounded by water molecules so they can't snap back together and make crystal again. So we don't see them. They're individual ions, and they're way too small for us to see, unlike crystals of salt or sugar. Now, eventually it gets crowded here, and there aren't enough water molecules to effectively make all the shields that we need to, and that point is saturation. So when saturation is reached, what happens is some of the solute particles will reform back into crystal, like this. So we see crystal being undissolved here and crystal being reformed here. The total amount of solid crystals that are present at any given time in saturation doesn't change, but which individual particles are part of crystal or part of the solution, that does change. It's kind of like juggling. The juggler has a certain number of balls in the air at all the times, but it's not always the same balls. Same thing here. There's a certain number of particles that are in solution at any given time, but they're not always the same ones, because crystal is being formed and unformed at the same rate.